hear me? Awesome. So my name is Jonathan Mercedes-Feliz. I am a postdoc currently at the University of Connecticut working with Daniel Alcazar. I do quite a lot of work on a lot of different things, but today I'm going to be focused on my work that I've done with fire. Specifically on the impact of aging, feedback, and fueling in affecting star formation. So before I start with the before I start about the topic that I'm going to be presenting, I want to kind of showcase some work that I've done. Specifically, we heard a little bit today about the effects of aging feedback in regulating massive galaxies in the high mass end. And so what we did here is that we introduced aging feedback into a massive galaxy at the peak of cosmic activity at cosmic noon on this massive galaxy that if we don't introduce aging feedback, stellar feedback is inefficient in actually shutting down star formation, so this becomes overcompact and overdense. So we introduced aging feedback to essentially quench the galaxy. So this is negative feedback. And so you can see that there's clearly stop star formation. This reaches very large scales, and we kind of have everything kind of surrounded with the aging winds. But when I compared this simulation with the same run without aging feedback, we did see some plausible signatures of positive feedback in a local scale. So what I'm showing here is a star formation efficiency map, which I've defined as the ratio of the star formation rate over the gas mass for each individual gas particle. And this angular region here is a local range that I'm comparing with the no feedback run. And you can see that we have this very nice region with high densities. So this is clearly very star formation, very efficient at forming stars. And in this region, when we compare that to the no feedback case, we have higher star formation efficiency as well as more molecular gas if we didn't have any AGN. And so what I like to call this is that we have essentially found local positive in the overall negative. That's kind of my coined term for this. And so you can look more into this in the paper here. And we decided to delve deeper into the analysis by comparing a whole slew of other simulations with increased aging feedback strength. And what we found is that in the simulations with the strongest aging feedback, we find essentially the strongest manifestation of local positive feedback. We find the formation of this ultra-dense stellar clump. And so this is just a stellar mass surface density map of stars that form within 35 million years of the quasar phase. And you can see that we have this kind of off-center clump. Of course, you can see that the AGN winds clearly affected the total star formation at the end. And so we wanted to see, okay, why is it that we find these stellar clumps forming? And essentially, what's happening here is that the AGN winds are compressing the gas. And essentially, they're pushing all of this gas with the outer ISM, and this is happening at such a short time scale, increasing the densities larger than the normal star formation of the entire galaxy, reaching super high densities, that this is happening faster than supernovae can disrupt them, and radio feedback is inefficient in actually destroying the formation of this clump. So this is kind of very similar to the feedback-free scenario that we've heard this week. And so that you can also look into that paper as well. So now we kind of know how aging feedback, black hole feedback, is essentially shutting down star formation. They're doing this massive damage to galaxies. But my next topic of the talk is essentially how do we actually jumpstart into this quasar phase? How do we fuel these black holes? And so we know that essentially black holes are grow through two different fueling mechanisms. We have mergers, where we drive a lot of gas into the central regions through these interactions. And we also have different secular processes, such as gravitational stabilities, that drive these gas down to the smaller scales. But I'd like to propose a new mechanism that can occur in these massive galaxies when they're transitioning into this, from their bursty to steady star formation phase that we've heard a little bit about this week. And so in fire, we heard about this a little bit. We do find instances of the galaxies having these bursty phases where star formation is super efficient, driving these multiple outflows, galactic scale outflows, driving all these different excursions of gas. So we're not allowing for the galaxy to kind of be stable for quite a long time, and you can see that after a certain point, the stellar potential well or the CGM virializes, whatever is your cup of tea, essentially stops this, allowing for the galactic winds to stay confined, and then you have kind of the steady star formation phase. And so fire simulations are predicting that essentially most of these massive galaxies should have this last final galactic scale outflow. And so my idea is that we have the entire ISM is completely evacuated, so you have a large amount of gas leaving the central regions. What about the gas that is essentially along the wind front here? The idea is that we can have a buildup of gas. So this is creating a pileup, a transient gas reservoir that later on will reaccrete. So can this pileup of gas reaccrete and feed the central activity? So not just can we fuel a quasar phase, but maybe fuel a starburst in the central galaxies. And so this kind of also coincides with the fact that in the fire simulations, black holes are kind of undermassive at a certain time. And this kind of correlates really well with the bursty phase where you have a lot of star formation driving a lot of gas, now allowing for that gas to fuel black holes. And once the stellar potential deepens, then you have the winds not doing anything, stellar feedback isn't efficient enough, and you have rapid black hole growth, allowing for the black holes to catch up to the scaling relations that we see. So how do we do this? So I showed you in the first few slides the work that I've done. This is using the same galaxy. So this is a massive galaxy at redshift 2. And this is essentially looking at the last instance where the last galactic outflow is driving out this amount of gas. And so I'm going to play this movie real quick. This is just a surface map where I have color-coded, encoded in here, inflowing, outflowing gas material. So inflow is blue gas, and outflowing is red gas. So as I play this movie, you'll see that we clearly get this last outflow driving out to super large scales, if the scale bar should be about 5 kpc here. And we've previously seen in simulations that use the same galaxy, but using Lagrangian hyperrefinement, we can explicitly see that there are strong gravitational torques that are driving quasar-like fueling rates. So we know that after this stage, we can have the ability to fuel a quasar. Okay, so now how can we visually see this in our simulations? So what I'm showing right here really quickly on the bottom-hand side is the cavity size as a function of time. And on the right top here, we have a bunch of volume mass densities. And so if I play this movie, you'll see that as the outflow is driving out all of this gas, we get this large cavity, and you see that there's this pileup of gas that's happening. We have a large reservoir, and once the galaxy starts to reform, the outflow stalls, we have this infall phase, and so you see all of that gas starts driving into the central region. I should note that this black line is the profile right before the outflow. So this is pre-outflow conditions. And you can see right when the galaxy has performed completely, we have much, much larger gas density. So we have higher fueling accretion. We have higher accretion rates overall. Boom. Yes. Nice. Okay. Oh. So now how do we actually, so I've shown you that the pileup is clearly happening. Now how do we actually quantify how much of that gas that is affected by the outflow, that is pileup gas, actually reaches the central regions? And so I implement this novel particle tracking algorithm. I'm not going to bore you with the details. It's a lot of work, but I've named it the PRESS algorithm for propel, reverse, and slow down. And what this algorithm does is essentially we are able to quantify the impact of pileup by tracking gas that originated from the outflow and any gas that hydrodynamically interacts with the outflow, specifically looking at any radial velocity changes. And so we do this, and the question is, does this work? So what I'm showing really quickly here are 3 particles that are essentially PRESS, where you see these time tracks. But first we have a particle that originated in the central regions. You see that it gets propelled out. So you see this kind of come out and then it kind of makes its way back into the central regions. We have this gas particle here further out. This white circle is the stalling radius. Essentially it's infalling, but then it reaches the outflow. The outflow pushes it out, so it reverses. As you can see, this is the radial velocity color code. It reverses its direction and then it falls back in. And ultimately, when they have this gas that is further out, CGM scales, that is coming in, as you can see, it slows down. Essentially, the outflow is decreasing its radial velocity change. So we clearly see that the algorithm is working, thank God. And so we continue to look at how this looks like with all particles. So you can see on the right-hand side, this is just one of our cases where we look at any gas that has had their radial velocities changed by over 100%. We can see that we have a clear propagation of the pile-up effect, I like to call it. And so algorithm's working, awesome. We know that there's a pile-up, okay, great. Now how much of that pile-up gas is making its way to its central regions? So I'm showing here really quickly is just gas mass density versus radius, where the profile here is the pre-outflow conditions, so before the outflow occurs. And the different colored lines here is essentially this beta parameter. So from purple to red, we're looking at stronger impact. How much of that gas has been strongly affected by the outflow? And so as I play this movie, we'll see that the outflow is happening. Okay, we're creating this pileup of gas. And for all these different colored lines, you see that clearly pileup is the pileup gas that has been affected, is clearly within the central regions here. It's most of it over 90, 80% at a certain time. And then once the galaxy starts to reform again, you see an influx of that gas. And still for quite a long amount of time, most of that pile of gas is making its way into the central 10, 100 parsecs range. And by looking at the ratio of gas that reaches within either the central 100 or 10 parsecs, where I have here the pile-up gas within some radial range divided by the total gas, we see that over in the first initial 50 million years, once the galaxy starts to reform, we have anywhere between 80% to about 40% of gas does make its way in there. It's important for the first 50 million years that we have most of that pile of gas is definitely making its way in here. And even after 40, 50 million years, we still have over 20%. Even if you look at very conservative numbers here, of gas clearly strongly impacted by this. So we do know that pileup is happening. We know that a lot of that pile of gas is making its way to the center regions, and we know that a good fraction of that makes it into the small enough scales that can either go into star formation or fuel the black hole. So I'm just going to leave my conclusions up really quickly. I'm done. Thank you.
Thank you.
I mean, wonderful illustrations. I mean, there's one thing I don't understand. This all makes sense to me if that gas that piles up is basically initially pressure supported. But if it's angular momentum supported, which is what I would have thought, given that you say you're in this late stage in which you have a settled system, then what happens to the angular momentum?
Great question. Thank you for this. I'm sorry. Oh no. Sorry. I was supposed to remove those animations. This is taking us a while. So I did look into the, into the angular momentum of the pileup gas. And so since we were able to track this gas all the way into the beginning, this is all gas that made its way into the central 100 parsecs at 60 million years. We tracked this back. And as you can see, the angular momentum doesn't change much. There's no overall net effect of the pileup on this. So all this is doing is that we're essentially just driving gas outwards, and any gas that's coming in is just being held. And once the outflow kind of dies out, then you're just allowing for that gas to kind of come back in. So we're not having any effect on the angular momentum. But we do see that the pileup gas starts closer and with lower angular momentum than overall gas that has never been affected by the pileup.
So the idea is that its pileup gas starts out with very little angular momentum to start with.
Yeah, but there's no actual overall change to it.
So while Pratik sets up, we can accommodate a quick question.
Very neat. So the old idea, going back at least 10 years to Dubois, Johann Dubois, is that you suppress the AGN feedback by supernova feedback until you get a deep enough potential well. Then you've got this new idea that you build up a pile-up of gas, which then can fall in and help to fuel both AGN and supernova feedback. Big question. What's the observational evidence for any of this?
At the moment, not much. So the hope is to look into this a little bit more deeper. I mean, because this could occur also in AGN outflows, right? And this is only looking at the last galactic outflow. Of course, there's been other outflows beforehand, or AGN outflows can also create this pileup effect. This is more of just a what's the word? A demonstration, essentially. Now the question is, can we see this observationally? Can I find any tracers that I can then connect with observations? I don't have the answer to that yet, but thanks for the question.
Let's thank our speaker again. Next, we have Pratik Gandhi telling us about POP3